thank you to all the organizers for inviting me here to give the talk. It's a really inspiring conference, I found that. Okay, so this is the title, explain a joint project in collaboration with Alain Connes. So everything I will say during this talk is obtained in collaboration with Alain Connes. Here is a schematic overview of what I'm going to say in this talk. So let's say that our latest development of the study of the Adel class space of Q has brought us to determine a correspondence between a algebraic geometric space which describes this quotient and the Adel class space, the original Adel class space, which with this analytic definition. Actually, for reasons which have to do with a connection with number theory and the description of the Riemann zeta function and the property of the Riemann zeta function, we take a quotient of the Adel class space of Q by the maximal compact subgroup of the Adel class group. So this is the double quotient that is going to be put in relation with an algebraic geometric description of it. In fact, the first algebraic geometric description that we obtained last year, it's in terms of what we call arithmetic site. So arithmetic site, it's a Grothendieck topos over B, and it is, well, it provides the first link, the collection of points, the category of points of this site. It provides us the first link with this double quotient. More recently, we extend the scalar, so the first Grothendieck topos, actually a semi-ring topos. I will explain later what I mean by that. The first arithmetic site, the first topos, had been recently extended by means of extension of scalars from B. B is the same B as the previous talk, is the Sierpinski space that Joyala has mentioned the first day. So B is the smallest semi-field of characteristic 1. It's the set that you saw before, 0, 1. It's a semi-field, and it's the smallest one. And so if we extend the scalar from this semi-field to R plus max, in fact, we obtain a new version of the arithmetic site. It's like, as I will say later, it's like in parallel with what happened to an arithmetic curve over a finite field when you extend the scalar and you pass to an algebraic closure of FQ. So this process produces a second description of this geometric space, which then the points of this scaling site, in fact, are in one-to-one correspondence with this double quotient. All these two sites, these two Grothendieck sites, are defined over a semi-structure of characteristic 1. So when I say characteristic 1, I mean idempotent semi-fields. So a structure for which x plus x equal x. And in order to link with the spectrum of the integers, we define a morphism of topoi, which maps a prime in spec Z to the orbit for Frobenius action defined over the points of these sites. Actually, on these orbits, we obtain very recently a Riemann-Roch formula. So then, so these slides will disappear now on the main screen, but will be left on these two lateral screens, so that you can, along the way, you can follow what the various steps. I hope you can follow the various steps I will describe. The issue at some point was that the integers, there is no connection, no straightforward algebraic connection between the integer and this very small semi-field of characteristic 1, idempotent structure. So in order to unify these constructions, we had to think of a categorical approach, which is through the theory of gamma sets, and in particular through the definition of the sphere spectrum in the easiest possible approach via gamma sets. So in this way, we obtain that both the integers and B, they become S-algebra once one uses a fully faithful functor which embeds both Z and B and the other instance of geometric construction over F1, and they all become S-algebra. So S, it's at the bottom, it's characteristic free, so characteristic 0 here, characteristic 1 here. S is characteristic free. It's a very basic yet fundamental structure which has already been developed in great detail by people in algebraic topology. But here we use the most easiest description of this sphere spectrum. So to do so, then we have moved, after embedding Z and B into the category of S-algebra, we obtain what could be a possible definition of absolute point or absolute algebra, so this sphere spectrum. So then I start to develop the definition, or recall the definition of the arithmetic site. So this is a Grothendieck topos. One start with, actually it's a very easy example, yet apparently carrying important information on the primes. So one start with the natural number, and 0, I add here the notation, it will come up later, and I denote by n cross the set of positive integers. So n cross is a small category with a single object, which I denoted dot, and the endomorphism of dot is n crossed. So we endow this category with what has been called the first day trivial topology. In SGA4 is called the chaotic topology. So then together with this trivial topology, we have a pre-sheaf over this site and cross J, Grothendieck site, and in fact, because of the use of the chaotic topology, any pre-sheaf is a sheaf. So here the two definitions are coincide because of the topology is rather irrelevant. So then any object here, any sheaf over n cross is in fact nothing but a set which is the image via this map of the unique element, unique object in the category, endowed with an action of n cross. So the description of the sheaves reduces to as simple as possible as a set plus an action of n cross. Then I go rather quickly through the definition of points in the Grothendieck topology. We saw the first day in the talks, the definition in general, but a point in this particular topos, it's a morphism of topoi from sets. So I denote star, it's a singleton. So I denoted by sheaf over the singleton. I mean, sheaf of the singleton is nothing but the category of sets, to an at cross. So which means nothing but the datum which we have when we provide two adjoint functor, P upper star and P lower star. P upper star, as written here, is right adjoint, so it's left exact. Sorry, it's left adjoint, so it's right exact. And we say that P upper star shouldn't be only right exact, but in fact it should be also left exact. So P upper star is exact as a functor. This point is in fact uniquely determined by a covariant functor after using the Yoneda contravariant embedding of n cross in n at cross. So then you compose the contravariant Yonedan embedding with the contravariant P upper star, and you get a covariant functor for n cross two sets. And the main fact is that this functor is what has been called in several talks flat, or filtering, which is equivalent to flat. This means that the category, this category is filtering. What does it mean? It means that you are given a set, which is the image of the point, of the dot point. This set is not empty. On this set, there is an action of n cross, and so the category that I'm alluding here is the category made whose objects are the objects of X, and the morphism in the category are, for example, so are described by element in n cross, which connects 2 points in X. So for instance, in this case, this is a morphism which connects Z to X. So to give a flat or filtering covariant functor, it's the same as associating, in this case, in this particular topos case, it's the same as associating a non-empty set, and the action of n cross, which is given with some property, being filtering. So the second step and the third step describes the meaning of filtering. So for any two objects in X, there exists a third object in X as for any filtering condition, so that Z is mapped to X and X prime through the action of two elements in n cross. These are elements, it's fancy notation, but in fact it means simply that there are two elements in n cross, one of which maps Z to X, and the second of which maps Z to X prime. So for any 2 points, there is a point above Z, and Z maps systematically, it's mapped to X first and to X prime second. The third condition for being filtering says that for X, in this set, and the K prime in n cross, so that X is connected, so X is described, so that the point Kx or Pkx equal Pk prime X, so then X is connects 2 points of the set capital X, then if this case happen, if this situation happen, then necessarily the action must be, the element which produce the element of n cross which produce the action must be the same, K equal K prime. So this is a easier version of what in general constitute the definition of a filtering functor in SGA4. So the issue here is to characterize the points of these topos. So then the first theorem of last year says that the category of points of n cross is canonically equivalent to the category of totally ordered group, isomorphic to non-trivial subgroup of Q. I added Q plus, and I will explain the reason. This is the positive part of Q. And the injective morphism of ordered group. What happened? Happened that if you are given a point, which is described in this form as map between n cross and sets, then on the set, which is what I call capital X before, now I call it P dot, over which acts n cross, this is going to become a semi-group, actually the positive part, of the totally ordered group as a subgroup of Q. And the addition in this H plus is provided by this formula. So if you take 2 points in H plus, the addition X plus X prime is given by the action of K plus K prime on Z for every Z, so that these two conditions are satisfied. So this makes sense because the category is filtering satisfies the second condition that we saw in the previous slides. Then what happened that H plus is the union, increasing union of subgroups, each of which is isomorphic to the additive semigroup of the integers. So by a process which is done by taking the symmetrization, one obtains H. So H is the totally ordered group which the statement refers to. So in H there is a positive part which is a semigroup, and the semigroup is provided to me by assigning a point, so assigning a set together with an action of n cross. In fact, this H plus, because the statement it's more precise, says that non-trivial subgroup of Q, so the second, this line explains how to interpret this abstract H as subgroup of Q in terms of a unique embedding that is provided by this map. So notice that K prime and K here refer exactly to this K prime above.
It's unique if you choose X.
Yes. Yes.
But just,
yes, it's okay.
May I ask some question here?
Yeah.
Because this monoid and cross is just product of infinitely many commuting z-positive. So prime numbers plays absolutely the same.
No, but the structure will come later. It will be the structure.
So this kind of identification somehow it's kind of not symmetric.
No, it's not symmetric, but the structure shift will give the additional structure. Very soon.
So yes, I will put in a remark the point when in fact I have to fix some structure sheaf on this topos, otherwise there are too many symmetries which are provided by the action of n cross. It will come up later, just a little bit later. The second part of the statement says that there is a canonical bijection of sets between points in n cross, so isomorphic classes of point in the topos, and the double quotient of the finite adels modulo the action of Q plus cross and Z hat cross. How is it defined? Well, it is defined by associating to a point, like described here, an adel. So an adel, in fact, the adel A that I refer in this formula is obtained by, it's uniquely associated, up to isomorphism, uniquely associated to one of these H. In fact, P is PH by the above statement. But this PH, H is in fact H of A. So this group, subgroups of Q, each of them is associated to a unique adel. And this adel, yes. Unique up to the hat cross, which is written here. And the definition of the H is given as the collection of a rational number so that A times Q, it's in Z hat. What that means that if you think about the adel, at the place P, say, this adel is going to be 0 if this H contains all the power of P. Otherwise, if it doesn't, there will be a point where, say, p to the minus mu is still in H, and p to the minus mu minus 1 is not anymore in H. Then I multiply, so the adels at p at that point will have description p to the mu. So then this is the definition of the adel, which is not written in these slides. But in fact, the formula here, the statement here, the requirement here makes the description of A rather visible. Okay, so here I come to the point that was raised a few minutes ago. In a way, we want to restrict the group of automorphism of the points of n hat cross arising from the endomorphism of n cross to avoid arbitrary permutation of the primes. So then, for this reason, we introduce a sort of structure sheaf over this topos. We introduce this. What is a sheaf? It's nothing but a set, as I said, with an action of n cross. So in particular, this is an example of a sheaf in the topos, Zmax. These are the typical semi-structure that people use in tropical geometry. Actually, in tropical geometry, people tend to use mostly Rmax. This is Zmax, but Rmax will be the same by substituting Z with R. So what one does is to change the addition in the classical description of Z So the addition becomes the max of two elements, and the product becomes the addition. This is a sheaf on the site, n cross j. And the action, for example, on minus infinity of n cross, so a minus infinity is fixed by the action of n cross, and the maximum between n and minus infinity is n, etc. So then over this sheaf, we define the action so n cross acts, we state that n cross acts on Z max by Frobenius endomorphism, which are described here, sending an element n cross, say k, to the Frobenius action, which is described by multiplying an integer by k. Actually, just want to comment a second, because it's not by chance that the algebra underlying this topoi is described in terms of semi-structure. These semi-structures are idempotent semi-structures, so they are of characteristic 1 in the sense I said at the beginning, x plus x equal x. So the reason is that in the previous slides, we had that a point was uniquely up to isomorphism characterized by a totally ordered group of Q. So this total order is reflected here, so in a structure which is idempotent. So there is a kind of tight connection between the notion of idempotent semi-structure and partial orders. So it's not a case that the geometry which represents the Adel class space, which is a space over in characteristic 0 now, is described at the level of the algebra by idempotent semi-structure. The definition of the arithmetic site, it's here. It's like when one gives a scheme and a structure sheaf. The scheme is substituted by the topos. The structure sheaf is substituted by a selected sheaf on this topos, which provides the restriction of the automorphism in view of the statement I made at the beginning. So here we are in the description of the arithmetic site here. So then next, what are the stocks of the structure sheaf? So then the semi-ring structure on Z max is compatible with the action of n cross, and then now the stocks of the structure sheaf with the following structure of semi-fields. So if I look at the stock of the structure sheaf at the point of this topos, which is connected, related one-to-one with this subgroup of Q, H, abstract group, yes. This is a canonical isomorphism, so the stock is canonical isomorphism to the semi-field H max. It's like by considering H, the H as an abstract rank 1 group, subgroup of Q, in fact, and then associating the corresponding semi-structure, which is adding minus infinity, make a variation of the addition rather than plus max, and the multiplication becomes plus. So what happened in particular for H equals Z, then the stock of the structure sheaf is isomorphic of Z max, and the point associated to this ordered subgroup of Q, Z, corresponds to an Adel, finite Adel, which is in fact made by 1, 1, 1 at every place. And the reason, if you remember the formula, the reason it's clear from what we are considering at this point here. So the Adels 1, 1, 1, 1, 1 everywhere corresponds to the point P attached, associated to Z. Well, then all what happened about the rest, this describes a space which has a sort of classical point. The remaining points, which are associated to subgroup of Q, rank 1 subgroup of Q, say H, they sort of, you might think of, obtained by specialization à la Weil. So there is a specialization going from PH to PZ. PZ is the Yoneda point, and the rest are non-classic points, which have some adels, not of this form, but more interesting description, so not this particularly easy one. So now in this setup, the field, finite field FQ, which is at the basis of the geometry in characteristic P, is played by this basic semi-field B, 0, 1, in which 1 plus 1 is 1 because we mean plus as the maximum between two elements. Yeah.
In this field, 0 equal to 1 or the...
No. 0 different from 1. It's a multiplicative monoid with the multiplicative identity different from the pointed, it's a pointed monoid, two elements distinct. We say that characteristic B is 1, meaning x plus x squared equal x, so it's an idempotent condition which determines the definition of characteristic here. B, it's embedded, so now B has no, unlike the case of finite field, when one considers finite towers or finite field extension of a given finite field, here there is no finite field extension, the first one of B. The first one, well, the important one we are going to consider is Rmax plus, which is the multiplicative version of Rmax. So then, because of the multiplicative version of Rmax is defined by 0, the set 0, infinity, max as a sum, and cross multiplication as the second operation. So remember that Rmax would have plus here. So here is the multiplicative version of Rmax. This is suitable, this version of Rmax is suitable for the description of the family of Frobenius automorphism of Rmax fixing B. So B has no finite extension, as I said, and B also embed in Zmax. This is the usual version of Zmax by sending 0 to minus infinity and 1 to 0. So if one think of, try to go in parallel with the geometry of, say, curve or a finite field, complete curve. So if the curve is complete, then there should be very, very few global sections, only the constant. So if one compute the global section of this topos, global section for the structure, I call structure sheaf, of the sheaf we fixed, Zmax. For this topos, this is the general definition of global section for in topos theory. This is nothing but 0 minus infinity, so it's isomorphic to B. So it looks like likewise what happened for a complete curve or a finite field for which the group of global section is reduced to the constant FQ. So in this case, FQ, as I said, is replaced by B. There is a second theorem now that put in what happened of this topos if we extend the scalars, if we pass to R plus max, if we look at the point of the topos better over R plus max. Well, the points of the arithmetic site over R plus max, the theorem states that is isomorphic to the double quotient, which is the space that I recall as the space that Alain has used in previous work, but modulo Z hat cross, and the action of R cross plus on this side corresponds to the action of the Frobenius. How does it go, this isomorphism? So then a point, as in algebraic geometry, is characterized, so a point defined over some field in classical algebraic geometry is described here by saying I have a map between sets, say beta is the topos of sheaves over the singleton, and Rmax plus 2n cross O. So then it's defined by assigning two components, a component which is given by a point here, And the second component given by, in algebra geometry, we go to in the reverse arrow. So it's like looking at the stock of O at the point, say, which we know to be H max for some H, subgroup of Q, to R max plus. And this is a local morphism, like in the previous talk we heard. So this is a local morphism, in this case, of semifields. So then the description of these points will be characterized by looking at the image, at the range of this F plus Schreck, whether, first of all, the range, one case is when the range of this local morphism is completely contained in B. And these are the points, in fact, of the topos over B. And these are in one-to-one correspondence by the previous theorem with an Adel class, a finite Adel class in the double quotient. Then there is the second case when the range of Fp sharp is not totally contained, it's not contained in B. So you go outside B. And in this case, what you get up to a parameterization of H, say H prime equal log of U for U in the range, U different from 0, you obtain not anymore a rank 1 subgroup of Q, but in fact a subgroup of R. And the association here, this association will map a pair, which is described by an Adel with, in the case of the finite, A's and the finite Adels, and the real number, to a lambda HA, which is in fact a subgroup of R, if HA was a subgroup of Q. So then, accordingly to the decomposition of the double quotient in two parts, the double quotient here it decomposes in two parts, by looking first at the finite Adels and then to the Adels which are not finite, with Archimedean component different from 0, one obtains the distinction between rank 1 subgroup which are contained in Q or subgroup of R, not anymore in Q. The condition here is as we saw before. So now I describe the arithmetic site with some detail, and then I pass to the description of the map of the morphism of topoi theta that I mentioned at the beginning. So this is a particularly important one because it connects a classical scheme, a classical topos, to this arithmetic site, and it is provided by, it's uniquely determined by a filtering functor. So theta is a morphism of topoi. Now, rather than n cross, we consider n cross union 0. This is at the beginning. I said sometime later in the talk I will use n0. So n0 it's n union 0. It's this non-negative.
Multiplication this time, not addition.
Yes. So then a morphism, geometric morphism of topoi, is determined by a filtering functor, theta star, from n0 cross, from the category, from the small category with a single object, and n0 cross, to sheaf over spec z. So it is given if I define what is this sheaf over spec z, which is the image of the unique element dot in the category. So theta, to describe this sheaf S, first of all, one thing what the theta is explicit. Theta determines a map between the points of the topoi. So a point here, it's a prime, a rational prime. And so a point here, in terms of the first theorem we saw, is it's a set with an action of n cross. So then the idea of the definition of theta comes by mapping P to the positive part of a subgroup, rank 1 subgroup of Q, which I denoted by HP. And it's like, I hear Alain saying that, it's like localizing at P. So taking a ratio of two integers, at the denominator you see all possible powers of p, and at the numerator you have integers. So then the zero, the generic point here, is mapped to 0. So HP, so this particular example of rank 1 subgroup of Q, as before, is going to be an H attached to an adele, AP, and the adele that turns out, which, I mean, HAP is described here like I wrote before, but the adeles attached to this particular subgroup of Q, when you see only at one prime all the power of P, is given by saying at the place P, the adeles must vanish because you have all possible power of P. At the other places, there is no issue, and you put 1. So this is the corresponding adeles in this case, and therefore the definition of the stock in view of this setup is given by, say, at the stock of this sheaf at the point P, because here we are at the level of sets with an action, is described by the semigroup HP plus, the positive part of HP. The sections, then you have to implement a good action of n cross on this sheaf, on the section of this sheaf. So the sections are given by maps from U, as usual in sheaf theory, to the coproduct for all P of HP plus, so that the stock, the germ of this section at P are different from 0 only for finite remaining P nu, and the action of N0 cross on this section is described by this formula. So N acts on Xi by acting on the germs of Xi at P. So this is the link between this classical topos, the scheme, spec Z, with the structure sheaf and the arithmetic site. So this, we sort of link two gadgets living in two different worlds. One is characteristic 0, one is in characteristic 1 by this map of topoi. And just add as a comment, the theory of High algebra that we'll see later provides a unifying framework for sheaves of commutative rings, like, for instance, the structure sheaf of spec Z, and the preimage of Z, here is max, not mads. So the preimage of Z max, which is a sheaf over this for this topos. Now I pass to the description of the scaling site. As I said, the scaling site, the previous theorem, one of the previous theorems says that if I consider the point of R plus max of this arithmetic site, then I get a 1-to-1 correspondence between this double quotient and the arithmetic site. Just passing to considering a point of R plus max is not sufficient, at least it's not we were not happy about this process. So we were looking for a topos whose collection of points right away, without extending, passing to R plus max, will provide a setup in which the collection of points are immediately in 1-to-1 correspondence with this double quotient. This is the scaling site. The scaling site is not as easy as is another Grothendieck topo, but it's not as easy as the previous one in the sense that the topology is not anymore the basic topology we used before. And so the goal is, as I said, is provide a geometric analytic structure over this double quotient. So we had to define a site first, and then go on. So now the category we use to define the site, it's denoted C here, and the object of the category are made by bounded open interval, possibly empty, inside 0 infinity. And the morphism between two objects are described, n cross, the action of n cross should be there in some form. So this is given by all elements in n cross, which maps a first open interval omega to the second one, if omega is not empty, otherwise it's the singleton. So on this open set, on this 0 infinity, this is the Euclidean topology that we use. So there is a jump in deepness with the use of the Euclidean topology. And so for every object in the category, then we consider the collection of all ordinary covers. So this is for the definition of the sieve of omega. So these are ordinary covers. So the union of omega I is omega, but omega I are open in omega. And the proposition states that K, in fact, defines a Grothendieck topology on the category C, first statement. And the second statement says that the sheaf, the sheaf over this site, so the topos, is canonically isomorphic to the category 0 infinity semi-direct product n cross, so of n equivariant, n cross equivariant sheaves on 0 infinity. So then you see immediately
These are sheaves in the ordinary sense.
ordinary sense, because over 0 infinity there is the Euclidean topology. There is a big jump of deepness at this point because the topology is very refined, and before was the trivial topology. So then this big jump on one side would bring a more interesting and somewhat more difficult interpretation of the points in the topos, but on the other side it should pay back to give us right away the structure that we had to work over in the previous site by passing 2 points defined over R plus max. So the scaling site, by definition, is the site C with the Grothendieck topology, J, which I've just described. And the scaling topos is the category of sheaves over this side, or equivalently in view of the previous proposition, and cross-equivariant action on 0 infinity. So the theorem of this here says that, in fact, then as before, one study the points of these topos, the category of points of these topos with support at 0, and then there will be a statement when the support is not 0. So the first case with the support 0 is the same as the category of point of n cross, which is nothing but the points of the first, of the arithmetic side defined over B. The second is when you look at the point with support different from 0, which is canonically equivalent to the category of rank 1 subgroup of R. So the points that we saw in the previous statement for the arithmetic site up to passing to those points of A defined over R plus max. So in view of this theorem, the goal was achieved in the sense that immediately we have that the collection of points is in one-to-one correspondence with the double quotient here. And as a consequence, there are canonical bijection of sets between the isomorphism of points of these topos, the points of the arithmetic topos defined over R plus max after extending, and the double quotient. So as I said, we pay a price because the topos, the Grothendieck topos is more sophisticated and so more difficult to understand from the point of view of the study of points. But the pay is that the result is automatic. As before, there will be a structure sheaf attached to this topos. But if we simply extend the structure sheaf Zmax to R plus max, and then for technical reason pass to the reduced structure attached to the tensor product, then this is not quite a sheaf anymore in this second topos because it's not the case that any pre-sheaf is a sheaf. So what happened is that the definition of the sheaf is obtained starting with this reduced semi-ring, which is simply the extension of scalars from Zmax to R plus max up to a reduced form, and then localize. So we have to localize this gadget, and this will be the stock of the sheaf. So the Legendre transform allows one to describe this semi-ring in details. What is it? Given in fact, more in general, given a rank 1 subgroup of R, H in R, an element in the tensor product, here is Zmax, but we can do this definition, the description in general, where I take H max. This is a Newton polygon, and as a Newton polygon in R2, it's the convex hull of the union of finitely many quadrants, xj, yj, minus q, where xj, yj, it's a point, it's the pair, describe a point in H cross R. And so the Newton polygon, in fact, is uniquely determined by the function max lambda xj plus yj, where lambda is an element in R plus. So now let's look at to describe the stock, and let's look at consider the ring of convex piecewise affine continuous function on zero infinity with slope in H and finitely many singularities, pointwise operation on this function. Then the proposition says that this reduced tensor product, called R, it's in fact isomorphic by means of the association sending the Newton polygon to the corresponding affine function Ln to the semi-rings Rh of convex piecewise affine continuous function, etc. So this is the tensor product description of in terms of the Newton polygon, and then the structure sheaf over this topos is defined by localizing the Rz, because in fact now rather than H, one look at Z, because we are extending scalar from the structure sheaf of the arithmetic side to R plus max. So then for any bounded open, I describe the section of this sheaf. So for any open bounded interval, a collection, the sections on omega are maps from omega to R max, and these sections are convex piecewise affine continuous function on omega with slopes in Z. The action is provided by this formula. And then through this definition, I look at the stock of also. The theorem says that if I consider a point in this topos associated to a rank 1 subgroup of R, H, the stock at this point, P equal PH, is the semi-ring RH of germs, now, of R max valued convex piecewise affine continuous function with slope in H. And yeah, so in the case of the abstract rank 1 subgroup of R, H, we consider the associate point with support in 0. So let H be an abstract rank subgroup of R, and let PH0 be associate point with support in 0. Then the stock at this point is described by the semi-ring H cross R max associated to the max plus construction. So this theorem gives the description of the stock under the attention that I'm paying the attention that is not enough to consider the extension of scalar of the above sheaf of the sheaf Z max for the arithmetic side. One has to be more careful, because in this setup, sheaves are not finite sets with an action. They're more sophisticated.
Sorry, why do you take germs?
Because
it's the stock. So, yes, this is corresponds to the theorem before that when we look at the stock for each. So then this is okay. So then the definition of the scaling site is therefore the scaling topos over which we fix this structure sheaf that I've just described. And in this case, I denoted A hat. This is viewed as a relative topos over R max plus, in the sense that the structure sheaves here are locally are structures over R plus max. The theorem, which gives the final viewpoint on the points of this scaling site, says that even if we look at the point of the scaling site over R plus max, this is not but a collection of points of the site of the scaling site. So this is a bijection of sets. And then there is a canonical projection from the scaling site to the arithmetic site, sort of by forgetting zero infinity and just retain n cross. And one derives, therefore, the final bijection of the points of the scaling site over R plus max, or the points of the arithmetic site over R plus max, and the double quotient that we were looking to study using algebraic geometric gadgets. Then the remaining part, here it's about a definition of Cartier divisor theory for this scaling site. So then the structure sheaf has a reduced structure, so immediately you can look at the embedding. So there is an embedding of the structure sheaf for any fixed omega. There is an embedding of the section in omega with the semi-field of fraction of omega. As I said, this is in view of the reduced structure that we impose for technical reasons over the structure sheaf of the arithmetic of the scaling site. Technical reasons, if you wonder what is behind this technical reason, is because this is in order that the Frobenius acts suitably on a tensor product in this framework of semi-structure. So then this embedding embeds convex piecewise affine continuous function into the semi-field of piecewise affine continuous function. So we lose here the convexity is not holding anymore. And the natural action of n cross on this sheaf of fractions defines a sheaf of semi-field on the scaling tops. So from now on, it's like a sort of generalizing the theory of Cartier divisors, because now you have a sheaf of sheaf of fractions in this context. And so then suppose you pick up a point on this topos, which corresponds to a subgroup of R, then look at the germ of this so an element in the stock, say F, the germ at H. Then there is a definition of order of this germ as H plus minus H minus, where H plus H minus it's described here by a limit, this limit. So imagine that you have to have in mind the Newton polygon point of view. So these are affine piecewise continuous function. You look at one point in which you sort of the slopes are different, and so then H plus and H minus gives you the slopes from the right and the slope from the left, and the two slopes are different because there is a singularity at the point. At that point, the function vanishes, and the order of vanishing is described by this difference. Okay, so now this part, it's about the statement I made at the beginning that the image of prime determines a orbit for the Frobenius action in either one of these sites. So then this is something that we don't see of spec Z, because in spec Z we see only P. We don't see the orbit of the Frobenius. So again, in pursuing this approach with the sites, arithmetic and scaling, is that now you can see how the action of the Frobenius on these sites act on points. So if suppose P is a rational integer and consider the subspace of points of the scaling site, Cp, which are this Cp, it's a collection of points with the property that each of these points is one-to-one correspondence with the subgroup with a rank 1 abstract group, which is isomorphic to one of these HP I described before in the process of giving the definition of H.
P is a prime.
P is a prime, yes. So HP are those are the subgroup of Q, the adel of which at P is it's 0, is when 1 otherwise. So schematically, if you take all of these CP, all these orbits, and these orbits embeds, so map to the image of spec Z via the map theta here. And this collection of orbits, in fact, it's a subspace of the points of the scaling site. And the points of the scaling site maps to the point of the arithmetic site. So this diagram is Cartesian. And so this collection of the orbits of the Frobenius in A hat cross defines the extension of scalar, defines an explicit way to see the extension of scalar of theta spec Z in A hat. So this is in analogy to the scheme that one obtained by extending the scalar of a scheme like spec FQT to the closure of the algebraic closure of FQ. So as I said, this description in spec Z was not visible. In spec Z, you have only P. You see only P. It's only when you move to an extension of Q that you would see the action, the Frobenius action, the orbit. But in this case, it's provided by this space. So now, what I said at the beginning is that each of these CP, they are like, they correspond to what classically would be an elliptic curve. And so then the next statement, it's about it's about a setup which is a definition of Riemann-Roch formula. Excuse me, I'm getting confused here. I just have to approach more. So then what I'm up to, it's a statement which defines a Riemann-Roch formula on these curves. We don't claim that these are tropical curves, by the way. They are curves defined over semi-structure, idempotent semi-structures, and we claim that they correspond to an elliptic curves in the classical context, because an elliptic curve in a classical context is described by a quotient of C cross modulo Q to the Z. In this case, the curve would be, rather than C cross, you would have R plus cross modulo P to the Z. So then the Riemann-Roch that we will see, will have, it's different from the classical one because the degree of the divisor is not anymore an integer. In this context, it is a real number. So then the map, which sending R cross plus to CP, induces a topological isomorphism from the quotient R cross plus modulo PZ to CP. Then what we do is CP, after all, it's a subspace of the scaling site in which there is a structure sheaf. So we pull back the structure sheaf restricted to CP to this quotient. So we call it OP. So this is the sheaf on this quotient whose section are piecewise affine convex function with slope in HP. 5 minutes, yes. And so then through the definition of the sheaf of quotients defined before, Kp, then one can prove that a global section has order 0, and the order uses this definition. So it's the order I defined before, pull it back to the quotient. And a divisor, like in the classical context, Cartier divisor is a section from CP to say H of the bundle of pair H small h, which is a subgroup of R and small h, and H are isomorphic abstractly to HP, and H small h is an element in H. This is in parallel with the theory of Cartier divisors for curves. And the degree of divisor on CP is this finite sum. I'm going a little bit faster, so I will put up the theorem. So the theorem says that if I pick up a divisor on these orbits of Frobenius actions, then the degree being 0 and also chi of the divisor being 0, chi is the map which is defined by looking at all possible, so all these H are lambda HP, so then there is a map, evident map sending H to HP modulo P minus 1 HP. So then if the degree of a divisor is 0, and it's also the image of chi, of D by chi is 0, then this principal. So then there is a notion of Jacobian for the curve and an isomorphism of the Jacobian of this curve with Z modulo P minus 1Z. Then, in fact, there is a definition for what classically we consider the sheaf of global section attached to a divisor over the curve CP. This is in parallel with the classical definition of OXD in algebraic geometry. And for each of these, for any section here, this denotes the norm at P denotes in fact the max of the p-adic norm of H lambda, as lambda is in HP. So then with this setup, one consider in fact a suitable notion of dimension for these modules. The difference between this case and the classical case here is visible again, because H0D in the classical context will be a vector space, say, over a field. In this case, there is no vector space anymore. This is a module, a B module, a semi-module, in fact. So one has to implement a correct definition for dimension. In this case, we took this definition, provided that in fact one proves this is the topological dimension, classical topological dimension, provides that one proves that this limit is finite. Indeed, it is finite. It coincides with the degree of the divisor for any divisor which is not positive, so positive divisor. Degree is at least is non-negative. And the formula that I alluded before, the Riemann-Roch formula, has this description. So you see it's like an elliptic case because the canonical divisor is not present. So you have this formula. So then just to collect together, I don't have the time to go into the S-algebra machine in details, but I want to say just a few words here. So as I mentioned at the beginning, these constructions are in characteristic 1, so they are in over-idempotent semi-structure. Spec Z, it's a gadget in characteristic 0. Likewise, the Adel class space or the double quotient. So there is no algebraic connection between Z and B, as I said at the beginning. So in order to gain a unique bottom structure, characteristic free, then we thought to use a certain construction which are very useful and known, very well known in algebraic topology, and we refer to the construction of S-algebra. So any of these categories, in fact, in particular semi-rings, and so rings, a certain construction in Arakelov geometry that Durov provided in the past, in the recent past, the theory of monoids, each of these algebraic structure embeds faithfully, here I consider, for example, the monoid and the semi-rings, embed faithfully as a subcategory of the category of S-algebra. So these hyperrings are there because in our project we also met hyperrings which are more sort of exotic form of algebraic structure than the one I talk about. So then with this setup one reconsider structure sheaf, for example, over spec Z, and one is able to reinterpret the structure sheaf as structure sheaf of S-algebra. So in this way, this is a unified point of view in order to be characteristic free. So in order to avoid to talk about characteristic P, characteristic 0, or characteristic 1, but to have a unique source categorical structure at the bottom, which is characteristic free and which provides the possible definition of absolute algebra or absolute point. So I think I stop here. I'm sorry, I don't have time to go into the details, but this is the life. Thanks.
Maybe we can take extra time for questions.
So I have two questions. One is about the scaling topology.
Yeah.
Because when you have all these identifications and then you say 0 infinity, semi-direct was with n.
Yeah, n cross.
How do you define in these terms a morphism in this category? What is a...
Oh, yes, but I just put a formula at the board. I put the formula at the board so you can see. Voilà.
Ah, okay, sorry. Okay. The other thing was when you discussed the Riemann-Roch theorem, you had this O of omega of convex functions and so on, and you said you embed it into semi-field of fractions.
Yeah.
But is it really an embedding? Because
Yes.
sometimes for some semi-rings.
Now the question, yes. In general, not. If you would consider the tensor product, which is you can define for two semi-structure where B, in general, it wouldn't be. And so that's why we pass to reduced structure. The reduced structure is like moving from a ring to the reduced ring. And then when you have a reduced structure. But this thing is there, it helps not only at that point, but as I said, also at the moment when you want to define, for example, we have a theory of correspondence, I didn't talk about this, on the self-product of the arithmetic site. And so this correspondence, in particular Frobenius correspondence. So the Frobenius for this type of, on the self-product, they do not behave well, they are not endomorphism because they are semi-structure. So that's why we use systematically in that development about the Frobenius correspondence also a reduced structure. So the reduced structure is like to avoid the badly behavior of the Frobenius on the self-product.
Because even the polynomial ring in one variable of a B, for this canonical mapping to the fraction, semi-field of fractions is not injected.
Yeah.
But here, you mean it for this O of omega, it is.
Yeah, because we sort of kill the idempot, the zero divisor.
All this is fine. I'm interested in the last thing where the compactified spec V over S.
Yeah.
Yes.
How do you see the real prime?
Oh, this is like in the construction of Durov. So spec Z bar.
Durov gets the wrong answer at the real prime. For him, GLN of Z, of the integers at the real prime is a finite group preserving the L1 polytope and not the orthogonal group.
Sure. But I mean, for instance, in our case, what we have is that when we take spec Z, it's no longer true that Z, a tensor product over S with Z, this is not isomorphic.
Okay,
so
that's fine. At Durov theory, it does reduce to the diagonal.
Yes.
But Durov gets the wrong answer at the real prime.
Yeah.
GLN.
Oh, sure, but we have the correct Picard group. So what we prove is that at the real prime, the Picard group gives you exactly R plus star, which is what you want, and which Durov doesn't.
Okay, but it's the L1 metric there, not the L2 metric. It's a finite group, subgroup of GLNR. You get the analog of GLN ZP and GLN QP is the orthogonal group sitting in GLNR.
No, okay, but I mean, we don't care about GLN at the moment. We care about the Picard group of spec Z bar. And what we have found is that with our construction with S, what we have is we have one parameter family of invertible sheaves. So, and this is exactly what Durov was missing, because he was getting Q crossed, which is not the right answer. So we get exactly the right Arakelov answer.
And a right Arakelov answer, but you want the L2 norm at the real prime, and you get the L1 norm. Once you start, like with gamma sets, with sets, 2 points mapping to 1 point, its linear extension is addition, and it's unbounded at the real prime.
If you want, you can take any norm. I mean, it will still satisfy the condition. Any norm will work. I mean, any convex set will work, of course. Like in Europe, any convex set works. So you can take M2 if you wish. But I mean, this was not the point. The point was to understand that when you write a convex inequality at the Archimedean place, the fact that you can take convex combination with rational coefficients will create poles coming from the denominators at other primes. And this is perfectly embedded in the system. Now, what the real thing, Katya didn't have time to can you put the cyclic homology slide? You see, the real important thing is the following. The real important thing is that we would be in the dark if we didn't have a very powerful cohomology theory, which is present. And thanks to the work of Madsen, Esselolt, and all these people, they have developed cyclic homology over algebras over S. So this means that there is an immensely powerful machine which is waiting to be used and has been used extremely successfully already by Essalod and Madsen. For instance, there is a recent result by Essalod which says that when you take an algebra over Fp, and when you look at it as an S algebra, if you look at the cyclic homology, you obtain exactly the crystalline homology. And moreover, you obtain the Fontaine theory when you do filtrations in the correct way. So, I mean, this means that there is this enormous machine which is available, and it's available in the largest possible context, which is the context of S algebras. So this is why we believe that this is right.
If you start with S algebras or like Durov's monads, you're obliged to use the L1 norm, not the L2 norm.
No, not in the module. In the module, you can use the L2 norm. You can perfectly use the L2 norm in the module because it's convex combinations that you are implementing.
In modules, yes, but the local ring, so to
No,
speak.
because I think this all you have this important tricks. It's about non-Archimedean fields. You really miss Archimedean.
No, not over S. Over S, we don't have the idempotent. When we are over S, we don't have an idempotent module by any means. No, the picture that you should have is that spec Z is still characteristic 0 or whatever, and then we modify it to something in characteristic 1, but it's not the same thing as talking about the Archimedean place. The Archimedean place is not treated in characteristic 1, by no means. By no means. No. It's the same idea as the idea of Scholz and all these people, Fontaine and all that, of passing from one characteristic to another. So this is the general idea, but it's not the discussion of the Archimedean place. I mean, we didn't discuss it at all here.
Technical question related to his question. Why do you lose convexity when you go to this, to embed into the field of fractionals?
You take the difference.
You take the difference. Field of fractions, the product is addition, so when you pass to the field of fractions, you take F minus G, so you lose convexity.
That's the second derivative is positive.
Yeah. And others.
Subtracting. Second derivative can be everything.